Is it on already? Oh, okay.
But it's not going to amplify. It's just to get the recording.
Yeah, but it's a invisible microphone or like a speaker.
Yeah.
All right. Yeah, I'll make a note. I'll just add it in.
So everyone will know
Yep, sounds good.
the things I shouldn't say. Yeah.
Here you go. It's best done.
Okay. Good afternoon. So welcome to the Power and Energy Systems Seminar. And our speaker today is Zach Feinstein, who is a system professor at the Washington University in St. Louis, not the University of Washington in Washington State. I saw the one of you is wearing the shirt. This is the University of Washington, right? Yeah. So WashU is a better among the two, a very prestigious private university. And before coming to WashU, Zach got his PhD degree in operational research and financial engineering at Princeton. And before that, he got his bachelor from Washington University in St.
Yep.
Louis. So we'll be very excited to hear the talk on how to use concepts and tools in financial engineering, risk measurement, risk analysis for analyzing the power grid. So let's welcome the speaker, and Zach, the floor is yours.
Thank you very much for that nice introduction. Thank you all for being here, and thank you for the invitation to speak, for me to talk. So as was mentioned, I'm going to be talking about the application of risk measures which are coming from financial mathematics and financial engineering, and using this for measuring the risk of the power grid. This is joint work with Alex Cassidy, who graduated from Washington University. He got his PhD in the spring, and Professor Neharai, who was his advisor. So if I can get control of this. Thank you. So just a brief outline of what I'm going to talk about. I'm going to start with just a motivation of the problem and motivation of the approach I'm going to take. And then I'm going to really go into the mathematics of these risk measures, what these set-valued risk measures actually, mathematically, the properties that they have, followed by kind of an efficient allocation rule. So how do you choose kind of the minimal cost point for these risk measures? Then I'll go through a very simple computational algorithm that we can use to actually work with these, followed by some quick numerical examples to demonstrate that we can work with these, we can get some interesting pictures, and finally a conclusion where we summarize what we talked about. So just to jump right in. Nope. So motivation. So really we have problem of large failures in the power grid. These happened. We had the 2003 blackout in the entire Northeast, as well as other occasions of this. These can come from just random failures, or it could come from a natural disaster or cyber attack. We don't distinguish between these events. They all can fit within our framework. And really it has to do with the interconnected nature of the grid. So if you take down one component in the system, it won't just stay localized. It can very easily spread throughout the entire grid to very large regions, as evidenced in 2003. But you can't really have perfect robustness. There will be occasions where failures do occur. So what we want to do is consider the risk of contagion. We want to figure out how do we prevent contagion from occurring to a certain high degree of probability.
And first time you use the word risk here, technically, just give us a definition or a working definition that we should follow the rest of your talk.
For what risk means?
Yeah.
So risk means essentially a failure of a system component. So in some sense, risk is someone that's demanding some electricity, some power, is not getting it.
But that's not the way we use risk in English. I mean,
Yeah.
the usual
So,
effective risk are like expected value and typically
well, so expected value would be your returns. So really depending on the problem that you're looking at, risk has a different definition.
risk is not the same as uncertainty, right?
No, risk and uncertainty are different things. So using variance generally is a poor choice for risk. But really I'm looking at kind of downside risk. So you have some goal that you're trying to reach, and any amount that you're below that is your risk. So this is a very general definition. It's an axiomatic definition that we're going to be working with. There's not really in English where we say, oh, you have high risk. That's actually not a very well-defined term.
And no two definitions are the same.
Exactly. So we're using a very general sense. And really in this talk, when we're talking about the risk we're talking about is usually going to mean that someone that is demanding power is not getting it. So how much below their demand are they going to actually receive?
Any good books to recommend for laymen?
For risk? Or so in the financial setting, I would recommend a book by Fulmer and Sheed on stochastic finance. But that is really, it's all focused on the financial setting. In terms of the power setting, I don't have any good reference book. Really, I'm coming at this from the financial engineering background and trying to come up with good analogies to apply that to the power grid. So when we're talking about risk, we have kind of these failures, and somehow this is going to impact society. It's going to impact consumers. It's going to impact us. If some line were to fail and it doesn't impact anyone, no one at the end user notices that there was a failure, I don't consider that a risky event. That can happen. It can happen in our simulations, but that's not going to contribute to our risk. And these failures can be precipitated, as I said, by weather events, natural disasters. They can be precipitated by cyber attacks. Or you can also have just stochastic renewable generation. So if you have solar power, weather events, you just have a cloudy day, you're going to have less power generation than you would otherwise. So if you were trying to replace a coal plant with a solar power plant, that would give you stochastic renewable generation and could precipitate one of these contagion events. So the goal of this talk is going to be to look at a novel approach to the measurement of risk for power transmission systems. And this is motivated by work by Professors Rudloff, Weber, and myself in financial systemic risk. So again, it's a concept where it's coming from these contagion events where the failure of one institution can spread to other institutions. Here we're going to be looking at the failure of one system component in the power grid spreading to other components, causing a much larger blackout, much larger loss of power than would otherwise be found. And it provides a framework that is actually model independent and generalizable. So it's not going to be specific to any transmission system. It's not going to be specific to saying I have coal plants that we know exactly how much power they're generating. It could be stochastic generation. It could be cyber attacks, natural disasters. This is very generalizable. It really is just a mathematical framework, but it provides a nice interpretation that we can work with. Finally, we're also going to look at kind of methods for how we can implement this. It's great to have mathematics. If you can't implement it, it's not very useful in practice. And it can be utilized for design or comparative statics of different systems. So if you were trying to design a system, trying to design a power grid, and you wanted to know which design will give you the minimal risk for the minimal cost, this framework will allow you to do that. And you can do it in a robust way over multiple different stress tests. So again, this is coming from the financial idea of stress testing banks. Here we're going to be looking at stress testing the different power grids. So jumping right into what the risk measures for power transmission systems would look like. What we have is we have some basic ingredients that we need to consider. So the first is a model of the system behavior. So this basically will follow Kirchhoff's laws or simplifications thereof. So for instance, at the end when I do numerical case studies, we'll look at the fast decoupled power flow algorithm, which I've been assured is a simplification of Kirchhoff's laws. We did that just for computational simplicity. We could have done it on the full laws. It would just be much longer to compute. And what this model of system behavior, what we really mean by that is some function which provides the distribution of outcomes based on the system parameters and stresses. So again, I'm working in a very generalizable, general statements. But if you want to think about this, you're doing Kirchhoff's laws on some random stresses. So you don't quite know what the system demand in a year will be, but you have kind of a good understanding distribution-wise of what it might look like. And then you can get a distribution of how much power is actually flowing, how much is given to the end users. Then we also, second component that we need is a notion of acceptability. So this is some criteria that determines when your random outcomes are, in some sense, good enough. So if you want to think about this, you can think about it as the tail expectation is above some threshold. And to do this, we really need an aggregate of the system. And for instance, in my numerical case studies, we're going to consider energy not served, so how much power that was demanded is not being served as the aggregate. That's just one that we chose because it has nice interpretation, but there's nothing special about energy not served. And finally, we need something called an eligible asset. This is really coming from the financial literature, but it's some way to measure performance. So in the case of the power system, what we're really going to be looking at is this vector of component capacities. So we're going to measure risk by finding the vector of component capacities that bring you to an acceptable outcome. So this is an input to your model of system behavior, your model, and you run your model and figure out, am I acceptable or not? Am I a good enough system? Is my tail expectation above my threshold? Or is my expected utility above some threshold? So we're going to go through kind of these basic ingredients in a little more detail just to give a better sense of what these mean and what these look like. So the aggregation function, so we're going to start with kind of this model of system behavior by moving this aggregate up into that. So what this aggregation function does is provides some sort of definition of severity of the system failures. So energy not served certainly satisfies this, and it quantifies the relative badness of the system. So we want kind of the severity to, we want to basically be able to aggregate the system in some way that will tell us when we are good or not. Mathematically, this is just going to be a function, I'm going to call it lambda, of this calligraphic x, which are all our system parameters, minus the system components, the capacities of the system components. Then this Rn is the capacity of each system component. So this is a vector. We can group components together and say all generators have the same capacity, all lines have the same capacity. So you can do dimension reduction. But in a mathematical general sense, this is just a vector in Rn of the system capacities, and it's mapping into L infinity. We really could have L0, but again, to just make this tractable mathematically, we're going to assume everything is uniformly bounded. And this is saying you put some stress, it's hidden inside this lambda or inside this calligraphic x, and this stress is going to tell you at the end you have some random output, some random aggregation to your system. We're going to assume that this aggregation function is non-decreasing in its second argument. So as you increase the system capacities, you're going to have an increased aggregation. So the more capacity you have, the better the system performs. And this is not necessarily as a system-wide increase. If one component is increased, you're going to at least not be any worse. This is part of the reason why we chose capacity as our eligible asset. It has this nice property that if you increase it, your system will perform better. In finance, the analogous property is cash. If you have more cash, you're going to perform better. So N is just how many components you have in the system. So it means how many lines you have, it could be how many generators you have, anything that you really could think of stressing, anything that can fail because they go over capacity, can be part of this N.
You use the terms so far: good, better, and worse. And is it a 0-1 type of game, or is it the continuity that you're
Well,
talking about?
so we don't assume continuity.
I'm
Yeah,
saying,
and acceptability is a 0-1 type of thing. It's you're either acceptable or you're not.
So it's okay. So,
But it's coming. So the outcomes, like energy not served, will generally be continuous. But the risk measure itself is a set, and it's telling you which capacities make you acceptable will be the outcome of this set. So we can put properties on closedness of this of the graph of this set valued function, which is a kind of continuity property. But in terms of just looking at one snapshot, all it's telling you is these are acceptable and these are not. It's a feasibility region. Is that okay? So some possible examples of aggregation. So I've talked about energy not served, and that's what we're going to use in our numerical case studies. But we could just as easily use kind of a weighted energy not served. So if you decide that industrial plants matter more than home users, than individuals, then you could weight the amount of energy that they're receiving more than you weight the amount for a normal user. You can make this nonlinear. It need not be a linear weighting. We could also use loss of load expectation, which I'm not an electrical engineer, but what I've been led to believe is the difference between energy not served and loss of load expectation has to do with a time component to how long the energy is not being served. We can also look at ratio of power served to power dropped, or you could just look at the total number of failures in your system. Any of these will satisfy our definition of an aggregation function. There's many more that could be used. These are just the ones that I'm aware of. And in particular, we're going to consider energy not served. But for most of this talk, we're just going to use this lambda notation.
So isn't energy not served just a special case of your second bullet?
Yes.
Is the weights equal to 1?
Exactly. Then we need this notion of acceptability. So we have this idea of a good system outcome. So an acceptance set is just some subset of your random variables, of your outcomes. And you want it so that if you start with something that is acceptable, start with some outcome that is acceptable, if you make that outcome higher, make it greater, you're going to remain acceptable. So really the idea is acceptance is this you have this downside risk notion. So if you do worse, you might leave acceptability, but if you do better, if your outcome is higher in terms of how much energy is being provided, for instance, then you're going to remain acceptable. And we're going to really take advantage of this in our computation to decrease computational complexity, which we'll get to.
Your addition there,
this is Minkowski addition.
A set?
Yes, this is Minkowski addition. So summation of elements. So you do summation of all elements. Really, if we write this down, if we say x is acceptable and we have z is a non-negative random variable, then x plus z is acceptable as well. So this is what we mean by that Minkowski addition. So this is just the mathematical definition of some acceptance set. And then in the financial mathematics literature, you can define a risk measure from an acceptance set, similarly an acceptance set from a risk measure. So some possible examples that we can look at, there's value at risk, average value at risk, utility-based shortfall, and optimized certainty equivalence. And I'm going to go through what these are in the next slide to give more details on this. But again, in our examples at the end, our numerical case studies, we're just going to focus on value at risk. Again, this one is very popular in finance, though mathematically it's actually not the best. It's non-convex, but we're still able to compute it, which shows that we have a very tractable algorithm. So value at risk, we consider some outcome is acceptable if its alpha lower quantile is above some threshold gamma. So mathematically, we have some level alpha, we have some threshold gamma, and then we want that the probability that z is less than or equal to negative gamma is smaller than alpha, and we take as our acceptance set all outcomes z such that this is true. So this is a very widely used risk measure in finance, which then was you can take the average value at risk, which really is taking value at risk, averaging it over all the thresholds lower than alpha, but then we can actually write down another definition. But this is the expectation in the alpha lower tail. So you condition on being below your quantile and take the expectation. And again, we say we want this to be above a threshold. This has nicer mathematical properties in that it is convex and it's actually sublinear. And we can define the acceptance set thusly. This is just an equivalent. There's multiple ways of writing down the acceptance set of average value at risk. This one is usually used. It's easier to use mathematically. Then we have utility-based shortfall. So now an outcome is acceptable if its expected utility is above some threshold. So again, your acceptance set are those outcomes such that your expected utility is greater than or equal to your threshold gamma. Or optimized certainty equivalent if the optimal allocation between the present and future value is above a threshold gamma. From this one, you can really see where the finance is coming in. We're not going to use optimized certainty equivalence in this talk, but they give a nice class of risk measures with nice properties. And if you notice, this looks very similar to the definition of average value at risk, because average value at risk is a specific example of an optimized certainty equivalent. But here we have a concave utility function, and we just want some level, some r, such that r plus your expected utility, where you're decreasing by r, is greater than or equal to your threshold gamma. So these are just examples of different risk measures that we could use. We're going to focus in this talk on value at risk. So if you want to just think about the lower quantile whenever you see this calligraphic A, you're more than welcome to do that. But there is kind of this axiomatic definition in the background. So just to kind of summarize what we have, if we just want to consider power lines, just to simplify further, we're not going to consider the generators failing. So we have little n power lines, and we can just have this big N be the set of all power lines. Then we have our vector of capacities is K, which is K1 through Kn.
What does that mean, capacity?
So how much energy can flow through a line before it shorts itself out, or however the...
Because we have the notion of transfer capability,
Mhm.
and that's a far more restraining
Mhm.
than the capacity. If you're saying that's the capacity of the transmission line, that doesn't matter.
Okay, so it's the
In other words, it's not an additive concept.
additive in which, so like we're not adding the capacities together. We are then going to run through the model and see how much power is delivered at the end. So it's a soft constraint. So we're going to say that at the very start, based on your capacities and based on how much power is flowing through, you have probabilities of an initial failure. And then after that, it's only if you go above your capacity, if some power flowing through the line goes above a capacity, does it cause a failure?
I think we usually call it line limits.
Okay, so these are line limits. This is me not coming from the electrical engineering field. So
What we call line limits are thermal limits.
Okay.
And so it's a big issue because since you're using Kirchhoff's law, the transfer capability is totally different than these capacities.
It's not defined on the transport function. It's for each line.
Yeah.
That is what one from N.
Yeah, but I'm saying that's not the real constraint. It's a transfer capability which is a real constraint. So the fact that he can run so much power on every line, he can still have a failure.
We haven't got into the network model yet.
No, but that's what I'm trying to say, that the transfer capability is what we need to, if he's talking about networks.
We haven't
Yeah.
Well, he said at the very beginning that he's using Kirchhoff's law. That was his introduction.
Should we wait a minute?
Yeah. So to get to that,
That's fine.
well,
I'm putting a warning sign.
okay, so I welcome these questions because this is not my background. So I've been using the term capacity coming from not an electrical background. This is something that I understand. But if you're saying that there's something that's more stringent than capacity that has the same, in English definition, the same concept, then yes, we would be using that instead. I was not the one that ran the simulations. This was me talking with Alex Cassidy, who was the graduate student, who does have more of this background. So in talking with him, I would use the term capacity. I'm assuming that he used the right actual definition in his work. This is coming from the layman's definition of capacity, same way that you were looking at the layman's definition of risk earlier. So if you just want to think about this as line limits or the transmission capabilities, that is exactly what this could be. Then we have our terminal statistic, for instance, the energy not served. And again, this is lambda of x and k. And this gives us our model of system behavior. And then we have the acceptance set of a classical scalar risk measure, this calligraphic A. And what we do is we require the power system to have capacities k such that the resulting outcome is acceptable. So what we're looking for is lambda of x comma k to be in our acceptance set. So we want to find capacities, we want to find transfer capabilities such that we have an acceptable outcome. So in a definition, we just have the risk measure R is a power system risk measure. It's a mapping from this calligraphic X, so our system parameters, including stresses, into this upper sets, so Rn and Rn plus. So it's just any set in Rn such that if you add in this sense of Minkowski addition, if we add the positive orthant, we remain in our set. And then the risk measure, this should be an X, that's a typo. The risk measure of X is just those capacities, those transfer capabilities, such that our outcome is made acceptable. So this is exactly our definition. And then we're going to just put mild assumptions on the combination of the aggregation function and the acceptance set just to exclude pathological cases. we're going to assume that there exists some transfer capability so that we are acceptable, and we're going to assume that there's some so that we're not acceptable. Without this, it's just a pathological case that you have either negative infinite risk or positive infinite risk. So we just want to exclude those cases. So this would be the situation where just every line goes down no matter what happens, no matter what capacities, transfer capabilities you put in the system.
So X will be the input, like the
Yeah.
event, and K is the system parameters.
So the X is can include kind of their network topology, things like that are in your X, as well as the load, the demand load, which can be stressed. You could have other stresses going on inside of X.
Then how do you model like the kind of events of interest?
So that would be inside of the X as well.
Okay.
So we throw a lot inside of X, which is why we just call it this calligraphic X. So instead of trying to say this is going to be a random vector or anything like that, we're just going very general, calling this calligraphic X, and throwing any parameter that is not the capacities into that parameter.
So in the bracket, that's a calligraphic X?
This is a calligraphic X in the
bracket of lambda.
For lambda.
Is that a calligraphic X?
So this is an X. This is an element of the calligraphic X. So calligraphic X is the space. Little x, or the non-calligraphic X, is going to be some element of that space. We can put some properties on these systemic risk measures. So we have that we have this monotonicity property. If we know that for any capacities K, any transfer capabilities K, the aggregation, if the aggregation of X is greater than the aggregation for Y, then the risk of X is going to be less than the risk of Y. Superset actually corresponds to a lower amount of risk. So the way to think about that is if we're just in R2, since these are upper sets, if this is R of Y, and this is R of X, that's below it. So you have the superset corresponds to a lower amount of risk. So you get that kind of counterintuitive idea. Usually when you think about ordering of sets, you think of the superset as being the larger element. But because we have these upper sets, we actually have the superset corresponds to less than or equal. We also have that if our aggregation is continuous with respect to the capacities, we get that the images, R of X is a closed subset in our image space. And we have two kind of convexity definitions. So if we suppose we have a convex acceptance set, which value at risk is not, but if we assume that we had that, then we have convex values if our aggregation is convex with respect to the capacities. And we have a convex risk measure if the aggregation is jointly concave. Aggregation is concave, sorry. And again, just think about the superset as corresponding to less than or equal, and you get the usual Jensen's inequality. So we do get this nice convexity property, which has to do with diversification. I'm not yet sure a nice electrical engineering version of this diversification idea, but it's a nice mathematical property for optimization purposes. So for example, if we considered energy not served and value at risk, then we'd have our aggregation function. We just do it in an omega-wise, defined in an omega-wise way. And we have our stresses x. We just take the omega, and we take the negative energy not served because we want this monotonicity property. Then our aggregation function is just, or our acceptance set is just the definition from value at risk. And then if we let Q alpha define the alpha upper quantile of energy not served, again, upper quantile because we're taking this negative, so we go from upper to lower. Our risk measure, which is just definition, is aggregation is acceptable. We can write it in terms of the probability that our aggregation is lower than our negative gamma, our threshold is smaller than alpha, or our energy not served is above that threshold gamma, probability of that is less than alpha, or our upper quantile is less than or equal to gamma. So we kind of have these equivalent definitions going from the axiomatic definition, the general form, to ones that are very specific to being energy not served and value at risk. So this is just one example of what this risk measure mathematically will look like. And then we have these definition of the efficient allocation rules. So as I showed, the risk measure is the collection of all acceptable capacities. And in particular, the capacities cannot be chosen independently of one another. So if you were to set one line to have a higher capacity, you might be able to decrease if you have enough parallel lines going in your system. You might be able to decrease the capacity of another and remain acceptable. So you can't choose these independently. And even though the risk, the set captures the essence of the risk, it really gives you where you're acceptable, it's really hard to communicate to a practitioner. It's very hard to say your risk is this entire frontier or is this entire upper set. That's hard for them to comprehend. So what we're going to do is consider a simple alternative and choose a point k star on the boundary of our risk measure and require that the capacities are just above that point. So we pick a point on our frontier and say, that seems like the best one. And how are we going to do that? Or this is a more conservative approach. It doesn't consider how things really fit together, but it's still going to keep us to be acceptable, and it's easy to communicate to say, you need your capacities to be this specific level and nothing above and nothing below that. So we define this by a lemma. So we just define this k star to be the argmin of some linear objective subject to an acceptability criteria. So we want basically the minimal cost for an acceptable capacity. So specific price of the capacities, which is given by this function w. So some examples. Of course, you can have w just be a vector of 1. So this is minimizing the system-wide capacity that you need. You could also consider, for instance, this w is to be 1 divided by the centrality. So the more central a line is to the system, the higher its or the lower its higher its cost would be. You want to more central, the lower its cost. You want to increase the capacities at the more central lines at the expense of the more peripheral lines. Or you can consider where they vary based on your actual stresses. So if you consider the variance in your stress, so the more random the stress to a specific line would be, you could have that line have a higher price or lower price accordingly. So higher variance in the component response corresponds to a higher capacity required. So just the more randomness you have, the more uncertainty, the higher the capacity that you'll require while remaining on this efficient frontier. So it won't necessarily be, so Pareto optimal is the entire efficient frontier. So this is just picking one point on that frontier that in some sense seems optimal in a minimal cost structure. And cost is kind of in quotes because, for instance, here you're defining your cost based on how uncertain the response will be. So you really can have it where it's just dependent on the network topology, or even just minimize the system-wide capacity, or you can have it dependent on the randomness itself in your stresses. So if we want to compute these things, As I said, we want to determine the minimal capacity required. So determining the minimal capacity requires the computation of the entire boundary of this risk measure. And really, we just need to check if our aggregation is acceptable. And we're going to simplify this by just doing it on points on a grid. So we consider some area of interest. We're going to put some grid on that area. And then we're going to compute this and try to find where we're acceptable. And to do this generally requires Monte Carlo simulation because these are highly nonlinear problems, or can be highly nonlinear problems, and highly non-convex problems. And in particular, we have the upper set, and this upper set will be convex if our aggregation is concave, and our acceptance set is a convex acceptance set. So what do? Here's just a very simple example. If we're trying to find this set, so this set that we have over here, we consider the area from -3 to 3 and -2 to 2. We draw some regular grid, and then we want to search for this line. So we're going to start by just going over the main diagonal and finding 2 points, one that's not in the set and one that's in the set, so that they are adjacent points to each other. Once we find those, we know this blue point is in the set, this red one is out. And since it's an upper set, everything above this blue point is in the set, so we don't need to check those. And anything below this red point is out of the set. So we've already reduced the number of points that we need to check by a large amount. And then from this blue point, which we know is in the set, we're just going to search to the adjacent points that we are unsure about. So we go through, and you can label each point as being either in the set or out of the set. And if you notice, we went through far fewer points than we have in this grid. Of course, you do run into the curse of dimensionality as you go higher. But one nice thing is this is easily parallelizable. So if you just take slices, you can run these in parallel, and it is still feasible computationally to work with. So we have these points, and then we can connect the points to find an inner and outer approximation. And depending on how fine your grid is, that gives you exactly your error bounds for this set. If you know it's convex, you can use this dashed line for inner and outer. In fact, if you know it's convex, the dashed line for inner and the solid red line actually give you the tightest bounds that you can find using this grid search approach. But usually convexity just looks nice, so we'd use the dashed lines if we know we have convexity. We'd use the solid lines if we don't know that we have convexity. But this gives you an inner and outer approximation with a known error bound, just based on the diagonal of one of these boxes. Yep.
What space are we in? Are we in the risk space?
So this is in the image space. This is in Rn. So here we did it in R2. In the algorithms we're going to show, we do it in R2 by dimension reduction.
But what are we measuring here?
These are the capacities.
Those are the capacities.
Yes. So we're looking for this set, which is our risk measure. So these are the capacities that are acceptable, is anything that's in this set. And we're searching for that set.
And generators are not represented?
So we can use generators. We didn't in our numerical examples, but there's nothing that says that they can't be included. This is just for numerical tractability. We didn't include them. So if we just look at our case studies pretty quickly, because we're getting towards the end. The first case study, we ran this on the IEEE 30-bus system with the fast decoupled power flow algorithm. We considered 2 groups of lines. This is our dimension reduction. We have high centrality lines and low centrality lines. So we just took the network topology, grouped the lines into either being high or low centrality, and then said each of the high centrality lines is going to have the same capacity, and each of the low ones is going to have the same capacity. Again, this was just for numerical tractability to run these in a short amount of time. This is not anything that's required for our algorithm. or 4-hour framework. Then we're going to consider energy not served and value at risk with the probability of a complete, where we consider value at risk with probability of a complete blackout being less than 5%. So that gives us our threshold and our quantile level as 5%. And then we consider two possible load shedding schemes, either complete load shedding or no load shedding. So just going to the two extremes, not looking at anything in between, and we'll see that we get some differences.
Is that for each load or is for the total system?
So for any time that you would potentially have load shedding, it would be a 0 or 1.
Let me understand what
Yep.
Complete blackout means. You have 30 buses there.
Yep.
And do we assume we have loads at every bus?
I believe so. So
Okay, so does it mean that every bus gets 0 of its load net?
So when we ran this fast decoupled power flow algorithm, there were times if the capacities weren't high enough, we would get complete instability of the system and it would crash. So we considered that to be a complete blackout. So when the algorithm would find that the system is completely unstable, everything would fail, that's what we consider a complete blackout.
You're using the word stable now in a dangerous zone. I don't know what that means because you're doing static problems.
Yes.
There's no dynamic stability involved.
So what we did is we did add in a fictitious time element. So we ran the system.
OPF only works for a snapshot of time. When you take a snapshot of the system, that's when OPF works.
So I'm just going to explain what we did. I don't know if it, again, I'm not an electrical engineer. So I'm just saying how it was run. And what we did was said there's some initial stress and some initial failures that come from that stress. And then we run this fast decoupled power flow algorithm to figure out how this is going to be redistributed among the lines that have not failed. If any further lines would fail because we have overcapacity on some line, then we say that line has failed, we take it out of the system, and we run the fast decoupled power flow algorithm again. And we just keep running this until it either reaches a steady state and there's no new failures, or every line has failed, or no energy can reach the end users anymore. So that's what we mean by a complete blackout. Whether that's realistic in the energy power system literature, I can't answer that because I'm not coming from that literature. This is just how we ran this system and how we determined a complete blackout versus not. So.
I think the dynamics is totally in terms of when you have this evolving process and then the lines will fail gradually and the system will become disconnected.
I understand, but we can do that kind of stuff in terms of connectivity of the graph, because this is simply a graph. There's no generators shown. So,
well, there's generators. We're just not going to consider the capacities of the generators.
Well, I'm not understanding the physical model because he's only looking at the capacity of the lines.
Yeah.
So if you don't take into account the generation, then I don't see.
Well, so we.
Have generation limits. So at the end of the day, there may be unbalanced.
Yeah. So we're just not in the risk measure. We're fixing what the power generation capacities are. We're just not considering that as part of our n dimensions in our image space. So they're still in the x, they're just not in the k. So this is just to do dimension reduction, simplify the system. So if we run this under the two different load shedding schemes, we have kind of this blue and red curve. If you notice, these are highly non-convex. And there's kind of these thresholds that appear. And this is if we just assume there's one initial failure, and the probability of this initial failure is weighted by the initial loads on the different lines. So we take the fraction of fraction of the capacity of the line to the load on that line, and that gives us a probability of this initial failure. And we get this is our efficient frontier, so everything above these curves is going to be acceptable, is an acceptable capacity. And if we notice, if we take rho equals 0, we have something that is monotonically better off. So we have the situation where we do know that rho equals 0, in this case, performs better than rho equals 1. If we consider now, we have one initial failure, and this is chosen uniformly, so it's not dependent on how the initial system is set up. We get a very different risk measure or set, but we still have that the risk of 0 is now even better. It's uniform, monotonically, strictly better than the risk at rho equals 1. Similarly, if we consider 3 initial failures, we get it so that's a little less flat. We get a little more curvature to our sets. But again, this looks fairly similar to what we had before. And then actually, if we have 3 initial failures, each chosen uniformly in our system, we get rho equals 0 is this red line. It's basically just the positive orthant with a little bit of curvature down here. But if you consider rho equals 1, the load shedding is set to parameter as 1. This is never acceptable in this range from capacity of 1,000 for the low importance and capacity for 1,000 in the high importance. So essentially, if we have this situation where we did the stresses in the way that I described, rho equals 1 is never going to be acceptable. So that is a pretty strong argument. Yeah, we have kind of in these cases, we have some nicer properties for rho equals 0. It's a little bit better. Here we get strictly better. And then if we just compare this to what some have done in the literature before, if we consider kind of these different cases, the 1 weighted failure, 3 weighted failures, 1 uniform, 3 uniform, we also have the 5 weighted failures. And in both their case and ours, the 5 weighted and the 3 weighted look pretty much the same. There's not too much difference. The difference is here the 3 uniform failures still looks the same as our 1 weighted failure. So this purple and blue look the same. But if you consider this picture versus this picture, they look vastly different. So we actually get more information by doing our risk measures than you would do by just considering a capacity multiplier, which has been done previously in the literature. So they just take every line, start with some capacity on the lines, and consider a multiplier of that capacity and find where you get this critical threshold.
So 1 is what we start with.
1 is what you start with. So here, there's, this threshold is somewhere lower than 1. So each of these would be acceptable in that setting. Now, if we consider the IEEE 118 bus system with a generalized network flow algorithm, so this one's not coming from electrical engineering. It's not coming from Kirchhoff's laws. It's just a generalized network flow algorithm. And then again, we group our lines into high and low centrality. We're going to call things energy not served and consider these as capacities. And then we're going to consider rerouting schemes. So if we actually had complete control over how we're routing the power through the system, we're going to consider how this changes our risk.
There I understand the capacity of the lines.
Yeah.
This is it kind of a Fulkerson, but
yes, exactly. So here we get something that's more convex. We couldn't prove that it was convex, so we didn't plot it as that convex shape. But if we consider 3 different versions of value at risk, we have 10% probability of 0 failures, 5% probability of 1 failure, or 1% probability of 5 failures. We notice that this 10% probability of 0 failures is monotonically better than the other 2 cases. This green one would come somewhere off this plot. This is for no rerouting. So we just, if there's a failure, nothing gets rerouted. It just runs once. If we consider full rerouting, So we reroute the entire system anytime there's any failure. We get that this 1% case, 1% probability of 5% failures is now actually monotonically better than the other two cases. So it's completely different than this no rerouting scheme. And then if we just reroute on one path, so we just kind of do a shortest path rerouting, we now get, again, the same ordering that we had with no rerouting, but it is monotonically better than the no rerouting case. So this is rerouting along the shortest path, and these are just 3 different risk measures that we computed, all based on value at risk. And these points, these X marks that we have in each of these plots, are as the minimal system capacity. So we just did the efficient allocation rules with the costs all equal to 1. And here's just under different load scheme, we get similar types of pictures. And again, comparing to this capacity multiplier, these all look the same, whereas we get very different plots based on what our risk profiles look like. So just to conclude, we consider a multivariate approach to risk. So this provides a full profile of the system risk that a single value could miss. And it's useful for the design because we're giving you as an output the system capacities. We give a pragmatic approach to the implementation in practice. So these are the efficient allocation rules. And then we consider a simple algorithm that we can use to actually compute these set valued risk measures by doing Monte Carlo simulation and a grid search. So just thank you. And this is based on 2 working papers, one that is on power failures and the other on financial systemic risk. Thank you.
Last questions for Zach?
So if you go back to slide 32, but could you explain between this slide and the next slide why, I'm just trying to work to understand why the amount of rerouting you do shifts the green line
So dramatically.
than the other lines. Yeah.
So it has to do with the fact that we're looking at this 1% probability. So this is really a tail event. So it's just looking at what happens in the worst cases. So if you do full rerouting, your worst cases aren't going to be as bad. Whereas if you're only rerouting on the shortest path, you can still have some really bad worst case. So that's really how why that one shifts so much more than the 10% or 5% is just really based on this worst case analysis to get that.
What's the equivalent of routing in financial markets?
So in financial markets, we don't have the idea of rerouting.
It would be good to know.
It would be, if I were to take a guess, would be kind of central bank, the Fed intervening in different ways.
Yeah, so we need a dictatorship.
Yeah.
Yeah, yeah, I guess if you have questions, Zach will be here,
I'll be here.
Staying around for a few more minutes.
Yep.
You can ask more. Otherwise, we really thank
Yep.
Zach for the knowledge on financial markets, how to mitigate risk in our lives and everything. Thank you. Thanks, Zach,
Yep.
again.
Thank you.